is still aligned with the centroid. Oh, sorry, P is still aligned with the centroid during what? Buckling. Okay, so we just distinct when it's free, right? Free, the P will shift away from the what? From the centroid. If it's pinned, P will still be aligned to the what? To the centroid. Okay. But when it's pinned, the moments are equal to 0, as you can see over there. Okay. Now let's look at the other one. Okay. Okay, let's look at the next one. So the next one is one fixed end and one pin end. Okay. So which is the fixed and which is the pin? Okay. You can look at the diagram. Okay. Or you can look at what? Deformation pattern. Either way. If based on diagram, you know at point A, right? We know that point A is the what? Is the pin, right? Because this is pin. And then you look at this end is fixed. Okay. Now I'm going to draw a green line. Okay, I'm going to sketch a green line. Okay, I'm going to put a green line to the force. Okay, and it's one line. So that's doing deformation. Okay, doing deformation. And when you see P is still aligned, okay, it is not free. Okay, it is not free. Okay, it's not free. It has to be either pin or built in. Are we clear? Okay, because if it's free, the P can shift away from the centroid. Okay, now, if you don't look at the diagram, right, how do you know whether is it fixed or pin? So where it's fixed, moment at point B is not equal to 0. At pin, moment is equal to 0. Now, the next thing I want to do is I'm going to sketch the deformation pattern. If you look at the deformation, I'm going to follow the diagram. It goes parallel with the what? With the centroid, and then it starts to what? It starts to rotate. Can you see that? So when that's the case, when it's fixed, theta is equal to what? 0. Okay. When m is equal to 0, theta is not equal to 0. Okay. So I do apologize. I did not write the before one. These are both what? Pin, and this is also pin. Does that make sense now? Okay, I hope you look at this and say, yeah, I see this now. Okay. Right. That's where today's course, what do we do? I enforce your by looking at elastic curve to identify what? Boundary condition. Okay, so now we apply what we learned in elastic curve and boundary condition. Now we apply into buckling. Okay, so now we look at buckling again. Let's look at the last one. Okay, I know this is very obvious. Both ends are fixed or built in, and we know that at point A, the moment is not equal to 0. At point B, the moment is not equal to 0. This is where we define both ends are fixed. Okay, and it's impossible to be free because now if I were to draw our centroid, right? The P is still aligned to the centroid doing buckling. So it's nowhere to be free. It's never free at any of the ends. Okay. So with this, what we can also see is down here, theta is equal to 0. Theta is also equal to 0. That's why the deformation pattern, they do it this way. So this is a line. It comes here, then it slopes. Okay, it slopes. And then when it come back here, it gets aligned again. So the slope theta over here, theta is equal to 0. Over here, theta is equal to 0. Okay, I need you all to get really comfortable with boundary condition. I understand that this is the first time you're seen boundary condition with deformation pattern. I need you all to grasp this concept as soon as possible. And it's not difficult. So with this, you can identify when it's a free. It's free when the P, the load applied, is shifting away from the centroid. That's where you have the P. When is it a pin? Is when moment is equal to 0. So the slope is not equal to 0. When is it fixed? Fixed is when moment is not equal to 0, but slope of a deflection is equal to what? 0. Okay. So I want you all to capture in this aspect first, okay? Because this is one of the difficult part regarding buckling. Okay. Now let's go back to the equation. Okay. So now we are going to go back to slide number, not two, to this diagram over here. Remember, from here, I detour you all. We did some sidetrack. Okay. So now we are going back into this equation over here. Okay. Now we're going back to this equation over here. Okay. So I'm going to paste. Okay. So we just been through elastic curve. Now we are going to go back. Okay. And then I'm also going to get this diagram back. I hope. And we are going to have this equation. Okay. So from here, okay, from here, so from here means we're going to start from here again. Okay. So we're going to apply elastic curve. All right. So we have EI d squared y over dx squared, which is equal to m at q, right? And this will be equal to minus py. Okay. So I'm going to rewrite this expression over here. Is where we have minus or d squared y over dx squared is equal to minus capital P y over EI. Okay. So with this, we are going to carry, or we're going to rewrite the expression d squared y over dx squared. And then we have plus by capital P y over EI. Now Py is a single term, okay? And the whole thing is equal to 0. So I'm going to call this I'm going to call this, rather than 1, 2, 3, I'm going to call this equation A. Okay? So we realize that this expression over here is known as a homogeneous, okay, homogeneous second order differential equation. Okay. So just to quickly recap, okay, just to quickly recap second order, okay. Okay, second order differential equation. Usually it has a d squared y over dx squared plus by b dy by dx. And then we have plus by cy. This will be equal to 0, where a, b, and c are constant. Okay. So we know a way of solving it is, we know that the roots, okay, is equal to minus b plus or minus b squared minus 4ac over 2a. Okay. Then what a form that we can do is we're going to let alpha is equal to b over 2a, and we are going to let beta is equal to square root b squared minus 4ac, and then we divide by 2a. But okay, with reference to equation A, okay, with reference from to equation A, we know that B will be equal to what? 0. And when B is equal to 0, we will get the general solution. Okay, the general solution will be complex conjugate roots. So the general solution, okay, all this, I think you guys did your math probably last year. Okay, is you're going to record this very quickly. Is equal to y as a function of x will be equal to e minus alpha as a function of x, and then you have c1 sine omega x plus by c2 cos omega x. However, we know that alpha is equal to 0 as b is also equal to 0, right? And take note that beta is equal to what? Square root of b squared minus 4ac divided by what? 2a. Yes or no? So what we realize that in our case, b is equal to 0, or from equation A, or with reference, to equation A, okay, we know that B is equal to 0